Welcome to Mathematics in the AI Era, a PSC series exploring the mathematical ideas behind artificial intelligence, information, and intelligent systems. In this episode, we move beyond vectors and discover how matrices transform information inside modern AI systems. In the previous episode, we saw how vectors represent information. But representation alone is not enough. AI must transform these representations to discover useful patterns. This is where matrices enter the picture, providing a powerful mathematical mechanism for transformation. A matrix is a rectangular arrangement of numbers organized into rows and columns. At first, it may look like a simple table. But mathematically, a matrix can encode relationships and perform transformations on vectors and other mathematical representations. Think of a matrix as a mathematical machine. Feed a vector into it, and the matrix produces a new vector. The transformation can rotate, stretch, compress, or reshape information, changing how that information is represented. Matrix vector multiplication combines the numbers in a vector according to the relationships encoded in the matrix. The result is another vector. This simple operation is fundamental because neural networks repeatedly use it to transform information. Matrices can perform familiar geometric transformations. They can rotate an object, stretch it, compress it, or shear it. In AI, similar transformations occur in abstract spaces, changing representations so that useful patterns become easier for the model to identify. Matrices can also change the dimensionality of information. A high-dimensional vector can be compressed into fewer dimensions, or expanded into a richer representation. This ability allows neural networks to control the size and structure of information at different stages. Every transformation creates a new representation. An AI system may begin with raw numerical data and progressively transform it into representations containing increasingly useful features. Matrices provide the mathematical mechanism for moving between these different representations. A neural network can be viewed as a sequence of mathematical transformations. Information enters as a vector, passes through layers, and is repeatedly transformed. Each layer changes the representation, gradually extracting patterns needed for the final prediction. Inside a neural network, these transformations are controlled by weights. When many weights are organized together, they form matrices. During computation, these weight matrices multiply incoming vectors, determining how information flows through the network. At each layer, the network takes an input representation, applies a matrix transformation, adds a bias, and usually applies a nonlinear function. The result becomes the input for the next layer, creating a powerful chain of mathematical operations. Without nonlinear functions, even many layers would effectively behave like one large linear transformation. Nonlinearity allows neural networks to model curved boundaries and complex relationships. This is what gives deep learning its ability to capture patterns in the real world. Deep learning means stacking many transformations together. Each layer builds upon the representation produced by the previous one. Early layers may capture simple patterns, while deeper layers combine them into increasingly abstract and meaningful representations. The mathematics may look simple, but AI performs these operations on an enormous scale. Modern hardware can execute billions or even trillions of numerical operations efficiently, making massive neural networks computationally practical. The deeper idea is that AI continuously reshapes mathematical representations. Raw information enters one space and passes through successive transformations, revealing structure, patterns, and relationships. Mathematics changes not only the numbers, but how information is represented. We now know how matrices transform information. But an important question remains: how does AI learn which transformations are useful? That takes us to calculus, gradients, and optimization. Join us in episode 4, and like, share, and subscribe to PSC.